Okay, so what we're going to do is we're going to start the fourth chapter today, and the first section is going to be solving quadratic equations. Now, most of this should be review from Algebra 1, but this concept is super important moving from this point forward for the rest of class. So I really can't stress enough how important these basics are going to be and how we really want to get to a point where we've mastered this skill to make not only this chapter easier for you, but the upcoming chapters as we move into the second semester and finish out the first semester in this. We're going to have two learning targets, the first of which is that you're going to be able to solve quadratic functions by factoring and square rooting when the value is 1. Okay, secondly, I can solve real-world problems by using quadratics. Now, as we went ahead and we did an activity kind of relating to this. We talked about the area of a rectangle and how the area of a rectangle can be split into length times width, where length is a value and width is a value. Okay, so as I am looking at the different work that we did previously, we had it split up. Let me get my paper quick. Okay, we had successfully split things up into rectangles, right? And we said, hey, this was us multiplying, but we figured out if we can find out all of this inside part, we can go ahead and find the side length, okay? The same is kind of true here, but eventually we said that, hey, we want to, we use tiles, right? We built rectangles out of the appropriate use using tiles, and then we figured out the side lengths based on that. And then I last ended with this one question. In your own words, what is the pattern that you notice that will help you factor without the use of tiles? Because although I think immediately it'd be absolutely okay and acceptable to use tiles to go ahead and factor these things, but it's not realistic all the time. As we can see in this example A, this value of 50 is that's so many little individual tiles for us to use. It's not a good use of our time. So we have to wean ourselves off of this and use a more algebraic method. So let's go ahead and look at some of these patterns to actually figure out what that is. Okay, so if we look at this one here, we have x squared plus 6x plus 8 factored into x plus 4 times x plus 2. Right? We went ahead and figured out that if I create an x squared tile here, and then this would be 2 x's, and here 4 x's, x, then we would end up naturally with 8 little 1's here in this corner. 1, 1, 1, 1, 1, 1, 1. So this is kind of what the tiles would have looked like. But I don't want to have to use the tiles. I need to wean myself off of this. So let's look at these patterns, right? So if I think x times x is x squared, 4 times 2 is 8. So, that's reasonable to think that 4 and 2 together gets me 8. X and x squared is 8. But what about these other parts, and how do I get the 6? What do we notice about 4 and 2 and 6? Hopefully you're identifying that, to get this number, I just had to multiply these two numbers. 4 times 2. Okay? And then here, to get 6x, that is 4 plus 2. So that's the pattern, as amazing as that sounds. Hopefully a lot of you were able to kind of come to that conclusion on your own. If not, I was here to tell you, and I just did. Okay, so let's go ahead and do the first one. So what we look for when there's no number here, that's important to note. So as I look at my equations, I have ax squared plus bx plus c. So let's identify what my a value is, my b value, and my c value. So when I'm asking that, I'm asking what's the number being multiplied by x squared, because that's in the a slot. So if there's no number here, what number is that? 1. If I'm looking for my b value, I'm looking for the value multiplied by x. So what number is being multiplied by x here? 7. And here, c, I'm looking for the constant, or the standalone value, which is 10. Okay, so this method I'm teaching you only works when a value is 1. So this method only works when my a value is equal to 1. So let's go ahead and do this. So when my a value is equal to 1, when I have 3 terms and my a value is 1, I'm looking for 2 things. Numbers that multiply to c and add to b. Okay, so therefore I'm looking for numbers that multiply to 10 and add to 7. Okay, so some of you may have this in your head, but some of it's not so easy. So what I can do is I can put a little 10 over here and start listing the numbers. Well, the first one is going to be 1 and 10. Is there any way 1 and 10 are going to multiply to 10? Yeah, they're factors of it. But is it the right pair of factors? Do they add to 7? No. So is this my combination? No. So let's go to the next one, 2 and 5. Does 2 times 5 equal 10? Yes. Does 2 plus 5 equal 7? Yes. So this is my factor combination, which is a great sign, and we don't have to check any more of them because they are unique to the trinomial. So I know that this is going to factor into x plus 5 times x plus 2. Okay, now there's a good way to check your work. I'm not requiring it of you, but if you really want to be precise and see how you're doing, here's the way. You multiply these using the box method, and you should get the same result. So let's go ahead and do that. Okay, so here I'm going to go ahead, and I'm just going to use the box method real quick to check my work. This is going to be x plus 5. This is going to be x plus 2. So x times x is x squared. X times 5 is 5x. 2 times x is 2x. 2 times 5 is 10. So when I add this x squared plus 7x, right, these would combine, 2x and 5x combine to 7x plus 10. So this is why the combination of looking for numbers that multiply to c and add to b work, because I'm multiplying these two values to get my c value, and I'm adding these values with an x to get my b value. Okay, so the part that can get a little bit difficult with this is when some negative numbers get thrown in there. So when I'm looking at this, we're still using the same. This a value is 1, so I can see for the numbers that multiply to c and add to b. So I'm going to multiply to c, which is negative 6, and add to b, which is negative 1. Okay, so now you need to think about this. You have to have some understanding of basic multiplication and addition and subtraction of positive and negative numbers. What's the only way to multiply and get a negative number? Well, a positive times a positive is going to give me a positive, so that's not it. And a negative times a negative is also going to give me a positive, so that's not going to work either. The only combination is going to be one positive and one negative. So as I look at this here, I know that the two numbers I'm dealing with, one is going to be positive and one is going to be negative. And so when one's positive and one's negative, I need to think about what is going to add to negative 1. Okay, so let's go ahead and think about the number 6. Just in general, 6. Okay, so the first combination is 1 and 6. So 1 times 6, if one of these is negative, I can get negative 6. No problem. So negative 1 and 6 is negative 6, but if negative 1 and 6 is that negative 1? No, it's positive 5. So what about 1 and negative 6? So 1 times negative 6 is negative 6, that works. But 1 time plus negative 6 is negative 5. So this is not my combination. So I'm going to move on to the next one, 2 and 3. So let's check when 2 is negative. Negative 2 times 3 is negative 6. That works. But it has to fix this one also. Negative 2 times 3, or plus 3, is positive 1. And I have a negative 1, so that's not going to work. So let's try when 3 is negative. 2 times negative 3 is negative 6. That works. But positive 2 plus negative 3, that's negative 1. So that means this is my combination right here when this is negative. Okay, so let's go ahead and write that. This would be x plus 2 times x minus 3. Okay, here's the hint. When this middle number is negative and this is negative also, you're going to want the bigger value of the two to be negative. Okay, let's do the next one. So again, our a value here is 1. So I'm looking for values that multiply to negative 21 and add to positive 4. So really, when I'm trying to get to 21, the only combination I have is 3 and 7. Well, you know what? I lied. We have 1 and 21. But just looking at 1 and 21, if one of those numbers is negative, is there any way I'm adding to 4? No. So this excludes this combination immediately. We can get to negative 20 and positive 20. So what about 3 and 7? There's a combination here that will get me to 4. I just have to be careful about the one I'm picking. So I'm multiplying to a negative, so one of these numbers has to be negative and one has to be positive. Okay, so I know one has to be negative and one has to be positive. Okay, so let's just check when 3 is negative. Negative 3 times 7 is negative 21. That works. Negative 3 plus 7 is positive 4. So this is my combination when 3 is negative. And similar to example number 2, that is similar to problem number 2, is that here our middle term, since this is negative, this middle term is positive, so we would expect our greater value between 7 and 3 to be positive as well. Okay, last one. What about this one? X squared minus 7x plus 12. Again, my a value is 1, so I can look for numbers that multiply to positive 10 but add to negative 7. Well, let's think about how is that going to work. Because I'm multiplying to positive, but when I add together, I'm getting a negative. This might be puzzling to you, but let's just kind of think it out. What's the ways that we can multiply to a positive? Well, the obvious answer is a positive times a positive, right? But there is another way. What's that other way? 2 negatives. So here I know I'm going to have a negative number times another negative. So I'm going to have x minus a number times x minus a different number. So let's go ahead and figure our combinations out. So here 10. So we could try negative 1 and negative 10. Well, when I add those together, I'm going to get negative 11. That will not work. Let's try 2 and 5. Okay, 2 and 5. Well, when they're both negative, they will multiply to positive 10 and they'll add to negative 7. So this is our very unique combination. This is the only one that would work here. And again, you can check any one of these using our box method. Now, often students, the hardest part is figuring out the combination, so I would recommend doing exactly what I did and write your number you're trying to multiply to, figure out a combination, figure out your positives and negatives and see if it works, and just kind of work down the list. At some point, you will find the right combination. Okay, so I know I went through 4 examples. I think they're all good for you because they all give you a combination of negatives and positives here that you will need to be able to do. Okay, so now's a great time to pause the video, check, try A, B, C, and D on your own, and check it with me when you are done. Okay, so let's go ahead and we'll check these, and I'll give a quick, brief breakdown of each of these because, again, this is what we call factoring. Okay, specifically, we're factoring when the a value is 1. I can't stress that enough. Okay, but I really want us to understand where these numbers are coming from. Here, it's x plus 5 times x plus 10. Because since my a value is 1, I'm looking for numbers that multiply to c and add to b. So let's check. 5 times 10 is 50. 5 plus 10 is 15. Letter B. Here I'm looking for numbers that multiply to negative 24, so I know I'm going to have one negative and one positive. And I'm looking for numbers that will add to negative 2. So here, since I'm trying to add to a negative, I'm expecting the number with the larger value to be negative. So here, negative 6 and 4 multiply to negative 24. Negative 6 and 4 add to negative 2. These cannot be switched around with the signs. This cannot be positive 6 and negative 4 because then this would be a positive 2. So this is the only combination that works. C, I'm trying to multiply to negative 24. Okay, and so 8 and negative 3 give me to negative 24. And 8 and negative 3 add to 5. Okay, so 8 and negative 3, what if these were switched around, right? Then this middle term would be negative 5, but that's not what we have. So again, only combination that will work. Okay, and then lastly here I'm multiplying to a positive but adding to a negative, indicating to me, because I know my basic multiplication facts, that negatives times negatives add or multiply to positives, but negatives plus other negatives are going to result in more negative numbers. Okay. So, hoping you caught on to that pretty quick, but what I want to pose a question to you is this. I'm taking one number and I'm multiplying it by another number. So just any two numbers, right? But the result is 0. So let's think about what does that mean. So when I'm multiplying numbers, I'm thinking about groups, right? Like 4 times 5 is 20 because 4 groups of 5 is 20. Or 2 times 3 is 6 because if I take 2 and 2 and 2, 3 groups of 2, I have 6 together. So here, if I'm multiplying two numbers and I get 0, what do we know about one of those numbers? So hopefully you didn't read on to our sheet and you're thinking about it and you know that it doesn't matter what one of those numbers can be anything, but one of those two has to be 0. The only way to multiply two numbers together and get 0 is if one of those numbers is 0 to begin with. And that's what we call the zero product property. The zero product property says when the product of two expressions is 0, then at least one of those expressions must be 0. In other words, if I'm taking two numbers, a and b, and I'm multiplying by each other, I get 0, then that means either a is 0 or b is equal to 0. So let's elaborate on this more. What if I take x plus 5 times x plus 2 and it's equal to 0? What do we know then? That means then x plus 5 has to be 0 or x plus 2 has to equal 0. One or the other has to be true. So this is what we call the zero product property, and it's how we solve quadratics. So let's just talk about it right now. How we solve quadratics is essentially 2 steps. Well, I take that back. 3 steps. The first one is set the whole equation equal to 0. Get everything on one side of the equal sign and set it equal to 0. The second step is going to be factor the side that has all the stuff on it. And then third is use the zero product property to split your factors, saying one of those factors has to be equal to 0. So, now that I verbally have explained it, let's go ahead and see what this looks like. So here I have 5. I have x squared plus 7x plus 6 is equal to 0. So I'm looking for the x values I could plug into this equation to make the equation equal to 0. So the first thing we want to do is set it equal to 0. Well, if you're asking me, this is already set equal to 0, so that part's already done for us. The next thing we need to do is factor the side. So I'm looking at this and I have 3 terms, and my a value is 1. So that means I'm looking for numbers that multiply to 6 and add to 7. Multiply to 6 and add to 7. Okay, so let's find our combinations. My first combination is going to be 1 and 6. 1 times 6 is 6. 1 plus 6 is 7. So there's my combination. So now, what I have here is I have 2 terms, and I'm multiplying them together, and my result is 0. So that means, based on the zero product property, either x plus 1 is equal to 0, or x plus 6 is equal to 0. Okay, so then what I can do from this point is, I can solve this equation based on all the other things that we've done in the past and same here. So I would subtract 1 and say x is equal to -1, or I can subtract 6 we get x is equal to negative 6. So either of these ones are going to be true. Often with quadratics, and we'll find this out in a later chapter, you're going to get two answers because this highest exponent is 2. But we will dive into that on a later date. Okay, so let's see what they truly mean to be solutions. Let me see if I can get the lights back on in my room here. Of course it doesn't work. Okay, so I'm going to go ahead and use a calculator, and all I am going to do is I'm going to write this equation, but instead of x, I'm going to have negative 1. So I'm going to have negative 1 squared plus 7 times negative 1 plus 6. It's equal to 0. Let's do the same thing, but with negative 6. So instead of negative 1s, I'm going to replace those with negative 6s, and they're also equal to 0. So again, these will have two answers. So let's relate this back to the graphs that we saw in chapter 3. What this means is I am going to have a parabola that at negative 6 and negative 1, my parabola is going to cut right through those numbers somehow. I don't know what the y values are, but when I have solutions, when they're set equal to 0, that means this parabola is going to cross the x-axis at negative 6 as well as negative 1. Trying to relate it back to what we did in chapter 3. This is not something you're going to need to do. I just need to see this work here with your two answers. Okay, let's do number 6. Okay, so now number 6 has a little extra because this one's not set equal to 0. Right, so when it's not set equal to 0, we need to set it equal to 0. Now one big hint I'll give you is I could subtract x squared and add 10x to get 0 on this side. But in general, that would be a bad idea because this x squared would then become negative. We want the x squared term, we want the a value to be positive 1 as often as we can. So instead of subtracting x squared and adding 10x, I'm going to add 9. So here I have x squared minus 10x plus 9 is equal to 0. I have 3 terms, and my a value is 1. 3 terms with my a value of 1 means I'm looking for numbers that multiply to 9. Okay, that multiply to 9, but add to negative 10. So I want you to think about what kind of numbers, and I'm talking about positives and negatives, am I going to have that multiply to a positive 9 but add to a negative 10? So think about that to yourself. Am I going to have 1 negative, 1 positive, 2 negatives, or 2 positives? Hopefully as you're thinking about this, the only way to multiply to a positive but add to a negative is have 2 negative numbers. So when I'm trying to multiply to 9 here, we get 1 and 9. Negative 1 and negative 9 multiply to positive 9. Negative 1 plus negative 9 is negative 10. So that works. So there's my combination, x minus 1 times x minus 9. Okay, and then I can solve. So let's go ahead and do that. So that means x minus 1 is equal to 0, or x minus 9 is equal to 0. So I can add 1 to each side to find out that x is 1, and then I can add 9 to each side on the other one and get x is equal to 9. And again, what does this mean in terms of its graph? It means that if I have my x and y axis, that at positive 1 and positive 9, I have a parabola. I have a parabola that will go through the x values 1 and the x values of 9 on the x-axis. Again, I don't need to see the graph. I'm just explaining to you further, give you a little better understanding. But this is the biggest thing, right? Set equal to 0, factor, solve each factor, set equal to 0. Okay, I'm going to pause the video, and then I think you should try E and F on your own and check in with me when you are done. Okay, so I did have a little typo here. I accidentally put a plus, but it is a minus. I tried to fix it. Okay, so here I'm looking for numbers that multiply to negative 28 and add to 3. The combination here is a positive 7 and a negative 4. Then, since I have my two factors, and when I multiply my two factors together, I get 0, that means x plus 7 is equal to 0. Subtract 7 to get x is negative 7. Here, x minus 4 is equal to 0. Add 4 to each side, so x is 4. Here, I need to subtract 14. I need this set equal to 0 for me to solve. So quadratics, that is the method you use. So when you solve other problems, you just try to get x by itself. When you're solving quadratics, the method is set equal to 0 and factor. So here I'm setting equal to 0, and then I need to factor. I'm looking for numbers that multiply to negative 14, but add to 5. Okay, I'm multiplying to a negative, so I'm going to have one positive and one negative. Positive 7 times negative 2 is negative 14. Positive 7 plus negative 2 is 5. So I'm going to set my first factor, x plus 7, equal to 0. Subtract 7 from each side to find out that x is negative 7. Here I'm going to have x minus 2 is equal to 0. Add 2 to each side, so x is 2. Okay. All right. Word problems. So these are going to pop up from time to time, and they will progressively get a little bit harder realistically. I'm going to zoom out just a wee bit so it's there good for us. Okay. So, a group of students from your school volunteers to build a neighborhood playground. So here's the diagram of our playground. The playground will have a mulch border along just two of the sides. So just this side here. So here's my playground, and right in here, that's my mulch border, just around two of the sides. Okay. Okay, the mulch border will have the same width on both sides. So this distance is going to be the same distance here as here. But we don't know what that distance is, so we're going to call it x. The length of the playground is 20 yards, okay, and the width is 10 yards, just the playground. Is there enough mulch to cover 64 yards for the border? Okay. So, if you think about it, the area of this is going to be its length. It's going to be its length times its width. But I don't know what the length and the width are in terms of just numbers. But if I knew x was 4, then this would be 14. And if x was 4, this would be 24. How did I get those numbers? I added them. So here I can say that this side here is length x plus 10. And I can say that this length here is 20 plus whatever x is, so x plus 20. Okay. So here, what I want to do is I want to take my length times my width is going to be equal to my total area. My total area, everything all together, is length times width. Well, I know what my length is. It's x plus 10. I know what my width is. It's x plus 20. Now, what is my total area? My total area is this playground part plus mulch. Playground plus mulch. So let's figure out what the playground area is. Well, it would just be 20 times 10, just the playground area, right? So 20 times 10 is 200. But that doesn't include the border. I want to include the border. Like, that's the whole point. And how much mulch would there be in this area here? Okay, we're hoping to fit 64 square feet, right? We want to know if there's enough to fit 64 square feet there. So let's go ahead and put there. Okay, so that means my whole total area is 200 plus 64 because the playground's 200 and we want the border to be 64. So here I'm going to have x plus 10 times x plus 20 is equal to 264. Okay, so again, to solve these kind of problems, what do I need to do? I need to have it set equal to 0. Okay, so first, let's use the box method to expand this out. X plus 10, x plus 20 This is x squared. This is 10x. This is 20x. And this is 200. So x plus 10 times x plus 20 is x squared plus 20x and 10x is 30x plus 200 is equal to 264. Okay? So now all I have to do is set equal to 0, right? That's the whole goal we're trying to do, is set equal to 0. So what do I have to do to set equal to 0? I have two options. I can subtract 264 from each side, or I can subtract 10x squared minus 30x minus 200 from each side. Which one do we want to do? What we would like to do is do what requires the least amount of work, and also we want our x squared to remain positive. So we're going to subtract 264. So here I have x squared plus 30x minus 64 is now equal to 0. So what's the next thing we want to do to set things equal, or after we set it equal to 0? So just like I said previously in the previous problems, we want to set equal to 0 and factor. So now we have to factor this. So my a value is 1, so I'm looking for numbers that multiply to 64 and add to 30. So let's go 1 and 64, okay? So I'm multiplying to negative 64, so one of these numbers has to be negative. Okay, so it doesn't matter if any of these are one of these is negative. There's no way any of these numbers are going to add to 30. It just doesn't add up. Okay, so that means this is not my combination. So I'm going to check 2 and 32. If one of these numbers is negative, can I get to 30? Well, yeah, right? If 32 is positive and 2 is negative, those numbers add to 30. So this is my combination here. Which one has to be positive? Hopefully you're telling yourself that the 32 needs to be positive because my 30 is positive here, so we know the bigger number is going to be the positive one. Or the bigger value is going to be the positive one. Okay. Now, after I have it set equal to 0, based on what we did in the previous problems, what do? I set each factor equal to 0. So here I add 2. So here, now I know x is equal to negative 32 or x is equal to 2. Now, these problems are a little weird, right? Because algebraically, we found two numerical answers, negative 32 and positive 2. But only one of these is the actual answer, because this problem has context. And so we need to put context, we need to assign some context to these numbers. For example, if I said, I want you to build a mulch border around that has a width of negative 32 feet, how would you go about doing that? Well, the reasonable answer would be, say, you're not going to do that because there's no such thing as negative distance. Distance is always positive, regardless of whether you're moving forward, backward, sideways, doesn't matter. Distance is always positive. So there's only one answer that we can have here, and realistically that border needs to have a 2 feet in width. Meaning that if I want the total area, this is going to be 12, x is 2, and 10 is 12, and our width would be 22, x is 2, plus 20 is 20. So that's the big core of what I wanted to do. Now what I want to do here is I just want to talk about square roots and simplifying them, because we will have to do this later on, and I just want some practice early as we get going. If I want to simplify a square root, I need to split square roots up into perfect squares times non-perfect squares. So what I want to do with whenever I'm simplifying a square root is I want to split it up into the square root of a perfect square times the square root of a non-perfect square. So let's go over the first couple perfect squares. How you get them is you multiply numbers by themselves. So 0 times 0 is 0 times 0 is 0, therefore 0 is a perfect square. perfect squares, PS. So 0 is a perfect square. 1 times 1 is 1, so 1 is a perfect square. 2 times 2 is 4, so 4 is a perfect square. 3 times 3 is 9, so 9 is a perfect square. I hope you're getting the gist of it, so I'm just going to write the next few perfect squares. Okay. So, is there one of these perfect squares that divides into 18 evenly? Specifically, what's the largest one? Because 1 is going to divide into 18 evenly, but that's not the one I want. I want the largest one. And the largest one for us is 9. So I'm going to split this up into the square root of 9 times the square root of 2. Where did 2 come from? 9 times 2 is 18. Okay, and then what is the square root of 9? Meaning, what is the number I had to multiply by itself to get 9? Well, the answer is 3, so this would split into this 3 times the square root of 2. Should have done this in geometry, a little bit in algebra 1, but let's do some review. Okay, so then let's go ahead and we're going to do the same thing, but this one has a fraction. Well, when I have a fraction, I can do the top and the bottom separately. So I can say that this is the same as the square root of 36 over the square root of 5. Well, so here I want to simplify the square root of 36. Well, 36 is a perfect square, so I can just say that this is 6 over, and then I want to see if I can break up 5 into perfect squares and non-perfect squares. Well, the only perfect square that divides into 5 evenly is 1, so that doesn't really accomplish a whole lot. So we're going to leave this as the square root of 5. Okay, rule of thumb in my class and most algebra classes that you will do is you cannot have a square root symbol in the bottom of a fraction. So now what I need to do is I need to multiply the whole thing up, or not the whole thing. I need to find what I need to multiply this by to make it a perfect square. So here I have 5. What do I need to multiply 5 by to become a perfect square? It looks like I could do 5, right? So here what I'm going to do is I'm going to multiply this by the square root of 5 over the square root of 5. Let's talk about why this works. Because normally I would say you can't just multiply a number by another number because it will change its value. Unless there's an equal sign where you can do it on one side and the other, you can't just blindly multiply a number by another. Well, there is an exception, but this exception makes a lot of sense to me because what is this number here, the square root of 5 over the square root of 5? What is any fraction where the top number and the bottom number are literally the same thing? 1. 6 divided by 6 is 1. 8 divided by 8 is 1. The square root of 5 divided by the square root of 5 is 1. When I multiply a number by 1, do I change its value? No. So this is like a mathematical legal move, which would be multiply by 1 doesn't change the value. The other options you could do is add 0 in strategic ways, which we talked about with the tiles and the sneaky zeros. Okay, so I'm multiplying by a sneaky looking 1 here, and here that doesn't really mesh, so this is just going to be 6 times the square root of 5. What is the square root of 5 times the square root of 5? Well, it would be the square root of 25. Well, what's the square root of 25? What number multiplied by itself is 25? It's 5. So this is going to be 6 square roots of 5 divided by 5. And that's my answer. Okay. Again, these won't really pop up a lot until probably the 5th section or so, but I just want to start getting us to start thinking about some of these things. So what I'd like you to do is pause the video, try H and I on your own, and check it with me. Okay, so here I square root of 96. I had to split it up into a perfect square times a non-perfect square. The perfect square that divides into 96 evenly, the largest one is 16. So 16 times 6 is 96, so that's where the 6 came from. The square root of 16 is 4, so this whole thing is 4 times the square root of 6. Here I have a fraction, so I'm going to split them up and do them each individually. The square root of 49 is 7, but 11, none of these perfect squares divide evenly into it, except for 1. And again, that doesn't really help us any. So what I have to do is I have to make this bottom part a perfect square by multiplying by the square root of 11 over the square root of 11. Again, this is my sneaky 1. Just like we had a sneaky 0, this is my sneaky 1. It doesn't look like 1, but the square root of 11 divided by the square root of 11 is 1. Okay? So then I multiply straight across. 7 times the square root of 11 is 7 square roots of 11. Square root of 11 times the square root of 11 is a square root of 121. Where did 121 come from? 11 times 11. 121. Okay? And the square root of 121 is 11. So this whole thing is 7 times the square root of 11 divided by 11. All right, folks. It was a pretty short section, but I do not want to diminish the importance of this factoring section. Factoring will not go away until our last chapter and you're done with this class. We will use factoring to basically solve every equation, maybe not every equation, most equations from this point forward. Okay, so you need to take and invest yourself in the time to go ahead and master this. Okay, it will take some time, but you will get it. Okay, otherwise, that's the end of this video. Go ahead and move on to the homework, and then I'll see you at the beginning, actually, of the 4-2. We're going to do an activity before we begin the lesson. Otherwise, I'll see you then.